Hello. Good evening. Thank you for traveling to Milan for the ICFP conference and FARM. This is going to be a pretty exciting event this evening. We have a keynote with Dmitri Tymoczko, who, as you see, is a professor at Princeton and external professor at the Santa Fe Institute. And he's going to be doing a combination of lecturing and improvising with four remarkable musicians: Lucia on piano, Cecilia Sur violin, Maria on cello, and Taehong Park on bass. Let's give them a hand. And you will see them all playing later this evening as well. So there is a schedule on the ICFP Farm website, which you can see, but I'll try to walk through it just to keep us on track. So we have our keynote lecture. After that, we will have a 15-minute break. And then we will have the remaining performances after the 15-minute break. So before I introduce Dimitri, I also wanted to give a special shout out to two very important people. First, May Milano, co-chair of FARM. Yay. And the indispensable Massimo Colombo, audio wizard extraordinaire. All right, let's please give a big hand to Dimitri.
Hi, everybody. Thank you so much. Thank you to all the musicians and to Steve and May and to Massimo. I'm really excited to be here. Okay, so today's talk is called Refactoring Musical Thought, and we will move back and forth between a little bit of talking, a little bit of playing, and then a lot of talking. So we're going to start with who am I? This is a little awkward because I have to have this laptop set up so I can reach it from the keyboard, but in a little bit I'll be able to move it closer. So the answer is I am exactly like you. Like you, I was programming a VAX in 1981. Like you, I call it Dungeon and not Zork. That's an old guy joke. Like you, I narrowly evaded capture for password harvesting back when I was in like 7th grade. Like you, I owned a PDP-8 in 1986. There are no actual pictures, but so this is a Bing image creator recreation, but this is pretty much exactly what it looked like. Like you, I understand the phrase, contravariant functors operate by precomposition. Except the big difference is my wife has strict instructions to take away my laptop if she ever hears the phrase, you know, I think I'm going to try to learn Haskell. So I don't have time in my life. I program to get things done in a really slapdash, quick and dirty way. Sorry, I know. Maybe another difference is I started playing music really early on. This is actually my first piece that I ever composed. I composed it almost 50 years ago when I was like 6. Would you mind playing it?
You're pretty good. You are some.
I'm so, well, but... Thank you so much. Because I was 6, it's called The Walking Dinosaur. Then, in my teenage years, I got super into progressive rock. I gave up classical piano to play electric guitar. I was interested in loops and stuff like that. And I was super happy. I went off to college. I thought I was going to study electronic music with this wonderfully weird professor named Ivan Cherepnin. But I found that everyone except him wrote this very dissonant music that embodied inaudible patterns. And so this was a little bit of a life crisis that I confronted when I was about 20, 21 years old. So what we're going to now do, now that you know everything you need to know about me, we're going to do a little musical interlude. And this is going to be the story of my life in 3 acts, the 3 acts I just told you. And so I'm going to exit PowerPoint now, hide it, and we are going to use this cool interface I wrote where it generates notation on the fly. So the musicians will be able to see the notes that I am playing through an internet connection that sometimes works. And we will be able to achieve coordination through and spontaneity at the same time. So we're going to play 3 short improvisations corresponding to these 3 stages of my life. Okay. Okay, the second one is like my high school phase. And in this piece, there's a little bit of extra nerdery in that all the pitches you hear are correlated with the rhythms you hear. And they're correlated in two different ways. They're correlated in frequency space. So sometimes you'll hear notes repeating, and the high notes repeat faster than the low notes in proportion to the actual frequencies of vibration. So there's a funny thing, which is rhythm and pitch are the same physically. And so you'll hear that on this keyboard. And then in the other keyboard, you'll hear the logarithm of that mapping, where the chords you hear divide a single time span in the same proportion to the notes dividing the octave. So those are two isomorphisms between the space of pitch and the space of rhythm, and both of them are in play here.
Okay, now back to the lecture. So I'm going to turn off all of these fancy audio devices so we don't have any interruptions. And I'm going to go back to PowerPoint. I'm going to say thank you again, Lucia. What they did is very brave because it involves an unusual combination of sight reading and improvisation. Okay, let me also just put down the piano stick so that you can see what I'm saying. See all my projection. There we go. All right, we should be set. Okay, so when I left college, I felt I had a dilemma. Do you write dissonant music and get good grades? Do you become a non-academic musician? I felt, I think accurately, that I'm fundamentally a guy who's good at academics, and so going the non-academic route would not be utility maximizing. The result is I actually gave up music. I got a fellowship. I went off to Oxford to do philosophy. I got kicked out of philosophy graduate school 2 years later, becoming an unemployed guy who is good at academics. So why am I here? I'm here because in recovery from this event, I ended up learning some stuff about music, which I would like to share with you. So I'm going to start by saying I'm not really a natural musician. A natural musician, like my friend Steve, who introduced me, is someone who hears structure, intuits how to reproduce it, and successfully does so. I hear structure, but I'm not always so good at reproducing it intuitively. In fact, there are a number of kind of simple patterns that I've carried around with me for decades, little lines I've heard or bigger questions like, how do you make that amazing McCoy-Tyner piano sound? And it's often taken me decades to really figure it out. So I compensate for my lack of intuitive musicality, I guess, with my rational brain. And so incompetence is my secret superpower. My friend Andrew Gelman, the statistician, points out that this phrase secret superpower is really interesting because the only allowable secret superpowers are things like incompetence, right? The baseball player never says, my secret superpower is I'm incredibly good at hitting baseballs, right? So probably I have some other virtues besides incompetence. In other words, I think the big problem is a good deal of musical knowledge is intuitive and not easily translatable into words. And this is actually a significant obstacle both for music scholars and music creators. Sort of the big problem in our field is around 1900. Many musicians quite reasonably lost confidence in the inherited musical ways of doing things, right? Musical culture is a bunch of arbitrary decisions. Do it this way, don't do it that way. It's not really grounded in anything other than tradition. And, 1900, when we had, relativity and Picasso and all that stuff, people were rightly questioning why do it this way. And a big event, if you know the history of Western music, a gamelan came to Paris in 1889 and totally blew Debussy's mind because he heard these scales you couldn't even play on the Western piano. And it just sort of forcefully brought home to him how much of what he'd learned in school was essentially arbitrary convention. And so the interesting thing here is because of this, composers got into the business of reconstructing musical knowledge, of being theorists, figuring out how music worked. And this led to a remarkable phenomenon, which is that errors at the level of theory could negatively impact musical creations. So musical creations could maybe be mistaken in a way you wouldn't have thought was really possible. And some, aestheticians would argue it isn't actually possible. But this is a really interesting feature about the sort of interaction of theory and art making in music. Okay, so now I'm going to report on what I think of as stage one, which is my pursuit of sanity and trying to bring some order to the business of making music. And so one of the just basic questions I
I started thinking about is what makes music sound good. And obviously, the thing to do is to Google it. And the cool thing is if you Google what makes music sound good, you get to my website as the first hit. So I'm quite proud of that. And so I'm just going to talk about a few really obvious and basic properties that contribute to the sense of musical order, musical tonality. I want to say I do not think that tonality is the only good kind of music. As you heard, I'm quite happy making atonal music, but for many people, pleasant soundingness and orderedness are kind of correlated. So to get you warmed up, I'm going to play you some random notes so that you can hear just what the sound of randomness is, hopefully. Okay, so those are 3-note chords randomly distributed over the piano keyboard. Oh, shoot, I shouldn't have done that. History, how about recent history? Okay, so now what I'm going to do is introduce my first sort of feature of ordered music, which I call conjunct melodic motion. And that just basically means that notes move by short distances in log frequency space. If you play it on the piano, your hand doesn't have to move very far. So now I'm going to play you utterly random chords, but each note is constrained to be near its predecessor. And I want to ask you, can you tell the difference? And I'd venture that almost everyone in the room can tell the difference between that one and the one before, because it's really not, it's not that hard. The other constraint, the next constraint, that we can think of that as a horizontal constraint in a normal musical score that constrains how notes relate to their predecessors and successors. The other one is a vertical constraint, and it says that notes that sound at the same time are structurally similar to the other notes that sound at the same time. Exactly what that means involves some music theory, so I'm just going to leave it unspecified for now. What I want you to listen for is randomly distributed notes over the piano, except that they have to be related to each other in the way that musicians think about musical relationships. And I guess what I'm going to do, I'm going to actually ask you to raise your hand if you think that you can tell the difference between this random set of notes with the structure and the completely random set we started with. Okay, just intuitively, without thinking too hard, how many of you think you heard notable non-randomness in that sequence? Okay, it's really kind of interesting. I'd say 20%. Steve, can you identify the harmony?
Well, this must be 0 to 7.
Okay, so there's a difference between the musically trained ear. He's right. It is, in fact, the 0 to 7 chord. I think what that shows is that the vertical constraint is very weak absent combination with the horizontal constraint. So now what I'm going to do is put them together and see if you can hear the resemblance, hear the additional sense of order beyond just the horizontal part. So for me, what was really striking about that is the realization that I actually think I hear significantly more order in that one than in the one where you just have the vertical constraint. So in some funny way, the horizontal constraint does not depend on the vertical one, but the vertical one is more dependent on the horizontal one. And that's a piece of useful composerly knowledge that we didn't really have because I don't know, it's just not really part of the music composition tradition to perform simple experiments like that. Okay, so we've got a horizontal constraint that says notes move by small distances. We've got a vertical constraint that says notes relate to each other in some way. We're now going to add a third one. In all of the random sequences I played for you, every note is equally likely to occur as every other note. Black note, white note, all equally likely. What I'm going to do now is limit the field of possible notes and only allow the white notes. Okay, so now I'm adding 3 constraints, the horizontal, the vertical, plus what I call limited macro harmony. The idea is a scale is a kind of higher level harmony, and we're sensitive to that higher level harmony, even though it's never fully present at any one time. So we're going to now hear 3 constraints together. Otherwise, the music is completely random. Okay. It's not going to make anyone any money, but it's starting to sound recognizable. It's like Stravinsky before he had coffee, right? Like woke up, goes to the piano, hungover. Maybe that's sort of what it sounds like. My next constraint is what we call acoustic consonants. So far I've been really neutral about what chords I'm using, just that they have to relate to each other. Of course, some chords have an intrinsic quality of pleasantness or restfulness or consonance. And so now I'm going to switch. I've been deliberately using an unfamiliar chord, and now I'm going to use the regular old major triad. And just to make things interesting, some chords are going to be randomly short, and some chords are going to be randomly twice as long. And we get this. Sounds like Billy Joel before he's had his coffee now. So progress of a sort. Definitely, it's kind of funny because my ear hears little melodic things. I hear little statements in there. And I know that that is just the creation of my ear because it really is completely random. So this is about where I was in about 2011. And talking to you just now, it occurs to me that the interesting thing about this talk is how I got to the next level. And that's where we're going to end up. And yeah, it involves category theory. What I'm just going to do is play you one little thing. So a big kind of result here is that really simple features matter, and in particular, scales really matter. So what I'm going to do is play you completely random music, except that the probability distributions are very uneven. So we're going to start with the what's called the G melodic minor ascending scale, but with E as the overwhelmingly most likely note. And then we're going to move in the middle to a more chromatic collection. And then we're going to move back to that same scale we started with, but now with D as the overwhelmingly most likely note in the collection. And you're going to hear a kind of A, B, A prime form. And I think it's really interesting how ordered completely random notes can be if you just sort of constrain the randomness a little bit. Some of you may recognize some of the sounds. Because I was being nostalgic and retrospective, I went and got these sounds and put them into the first piece, the first improvisation we did. Okay. All right, it's still not going to make you money, but it might get you a university job and they will pay you the money, so. All right, so here's where I was. I wrote a book called A Geometry of Music. I talked about these 5 basic properties of pleasant sounding music. They're all very local properties. I think looking at them now from the vantage of, 12 or so years, I feel the limitation of the perspective, right? Where's the higher level stuff? I wasn't ready for that. A big take home was that scales are really important musical properties. If you are a musician or are curious about these things, I have a website called madmusicalscience.com. And if you go, there's a lot of websites there. There's a kind of fun scale finding website. Turns out that there are just 7 kinds of scales that contain all the chords you can make that don't have 3 adjacent piano notes in them. So everything that's not chromatic, you can go here, put in any chord, and it will find the correct, find the scales that have those chords. You can use this to train yourself improvisationally. If we had more time, I might just randomly do an improvisation based on scales, but I'm conscious of the fact that we need to get you out of here. But so scalar structure goes a lot of the way toward getting you something interesting. That last piece that I played for you, the little random demonstration, I always tell my grad students, your music should never sound worse than that, right? Because that's randomness. And so if your music sounds worse than that, that means your effort is actually contributing negative value to the output. And I mean, I'm not going to toot my own horn, but I've definitely heard pieces that I liked less than that, right? So, okay. There's another kind of cool thing about scales, which is they have a geometry. So these are the most common 7-note scales that exist in the Western tradition. My friend Rick Cohn, a mentor, he told me about this bottom square. He said, oh, check out this square relating the things. And I was able to realize that if you rotated the square, you could stack it on top of itself and get a series of 12 cubes linked face to face that circle back to each other. And when I first figured this out, I built a model out of marshmallows and toothpicks. There's also another really interesting question. So we've got these 5 basic local constraints, local properties of pleasant sounding music, whatever you want to call them. You might ask, like, how can they fit together? It's not obvious that they all can be. There's an optimization problem, right? It's not obvious that optimizing one is going to allow you to optimize the other. And so this was the beginning of a really interesting story that leads to a whole bunch of interesting connections between symmetries, geometry, and configuration spaces. So we can think of a pitch, a point on the piano, as an integer, and then the notes between the piano notes as rational numbers, fractions, or real numbers. These, you just get them by taking the logarithm of the fundamental frequency at which something is vibrating. An ordered sequence of pitches can be represented as a point in Rn, right? That's not a surprise. Many musical concepts can be represented as equivalence classes of ordered sequences of pitches. For instance, when musicians talk about chords, they usually mean a set of tuples related by the symmetries of octave shifting, which allows you to move any note up or down by octave, and permutation, because when you ask, what's a C major chord, people say the notes C, E, and G. They don't mean this one first, that one second. It's an unordered collection, right? So you can write this down. This is our equivalence class. This thing is equivalent to this thing. We permute the indices and so on. So what happens if you start with a Euclidean space and then fold it up by gluing points together? You get something called an orbifold. This is a singular quotient space. These things are exciting for a number of reasons. They were really popularized / invented by a guy named William Thurston in the 70s. They show up in string theory because people want to take the quotients of the higher dimensional, I forget how many. It used to be cool, right? But 11 dimensions, they got to fold up 6 of them. So whatever, 10 dimensions. But they would have orbifolds. So orbifolds, like these spaces have singularities in them, and that makes them non-classical as geometrical entities. And the structure of these spaces embodies the symmetries that you use to create them, okay? And they tell you really cool things about how the basic components of tonality can fit together. So let me just pause the PowerPoint and try to show you some goodies from this period. I've got to restart Max, and let's go over to source code, Max MSP, chord geometries app. And once you're ready, chord geometry source. It's this guy. We'll make some alarming gestures at first. Okay, so for instance, what happens if you take a two-dimensional plane that represents ordered pairs of pitches and you fold it up to represent octave equivalents? Well, that gives you, that octave equivalents are translations, so that gives you the two-dimensional torus. What happens when you fold the torus in half to glue together the two orderings of every pair on the torus? Anyone know? I bet someone here knows. It gives you a Mobius strip. So the space of two-note chords is a Mobius strip. Okay, oh, let me press D. Ah, there we go. So when musicians are playing on the piano with two fingers and categorizing those two-finger sonorities using normal musical concepts of a chord, we are navigating through a Mobius strip. And so each point here represents a pair of pitches. And if you move them in parallel, you move horizontally, and you'll see that as you move off the top right, you reappear on the lower left, so that's why it's a Mobius strip. It's not actually, it's not actually just a Mobius strip. The boundary of the strip has these orbifold points, so they are singular. And so what that means is line segments in the space sometimes look weird. That's a line segment. The line segment reflects off the mirror and returns to itself. And you want to think of that thing as a line segment, which you can't do using classical geometry. So these things have, there's one of these for every dimension. If you want to talk about three-note chords, they live in the three-dimensional analog of a Mobius strip, which is a twisted triangular prism. And we can glue together translations in this space. And then you get, this is the space of three-note chord types, which is a little cone, and this is the augmented triad, and Western music hangs out here near this symmetrical point. And actually, we built one of these. There used to be one of these, I think it's still there, in the Museum of Mathematics in Manhattan. Each of the balls representing the different types of chord is a theremin, so you can touch the major triad, and the sculpture plays major triad music. So this is a really cool way of creating new musical interfaces. And so what I want to just do is show you an interface I created called Beacons. And I'm going to play you a little bit. So Beacons allows you to put blinking lights in the two-dimensional configuration space of ordered chords, and it basically blinks back and forth between its X and Y coordinate. So it's a video game, and I'm going to play you just a little excerpt of me improvising with my video game with my friend Rudresh Mahantapa, the world's greatest alto saxophonist. I just want to give you this so that you have a sense of the possibilities of this configuration space approach to thinking about music. One could do a similar thing where the Mobius strip or the flat configuration space was a stage and a dancer's position was being mapped to, in a rigorous way, to these two-note chords. Okay, we'll play this. We won't play all 15 minutes, but just a little bit, 11 minutes. Okay. I wish we had time to play all of it, but we've got our functors to get to, so. All right, so this is this cool mapping between space and music, and the cool thing is that the spaces you get are often non-obvious. Okay, so that's like stage one. That's what occupied me maybe till around 2015, my pursuit of sanity. And now we're going to get to stage two, which is insanity's pursuit of me. So after a decade or so, it started to dawn on me that the reasoning involved in geometrical music theory was not actually geometrical. And I have to say, the person who first started me thinking about this is this wonderful eclectic polymath named Carlos Zapata Caratala, and he has something called an interdisciplinary society. They invited me to give a talk, and I gave the talk about the geometry stuff, and he was like, you know, I think you could categorify all of this. And I was like, whatever. But then, you know, over the years, that little bug kind of brainworm started tickling my brain in the right way. And he was right. So basically, everything, all of this, sort of the whole thought process, you can reformulate it if you get the right, you can take what's going on when you're making these singular orbifolds by folding up Euclidean space, and you can reformulate it as a theory of symmetry groups acting on groupoids. And this actually provides a very profound generalized perspective on symmetries. One that just like really any symmetry group acting on any groupoid, which could be a little discrete graph or it could be a complete space, it doesn't really matter. You can work out what I was doing with voice leading geometry in complete generality. And this may have some interesting application outside of music. I'm not sure about that. So I just finished my second book. I have to write a third book. My third book has a little concept map, and here it is. I am aware that this does look, we're starting to push the crackpot boundary a little bit. I have done the normal sanity checks. I've run it by algebraic topologists, and they say, yeah, okay, makes sense. So Over here we have a symmetry group acting on what I call a coordinatized groupoid. You have to double your groupoid. That's one of the secrets. And then you make a special kind of quotient called the orbifold quotient. And it turns out that the symmetry group acting on coordinates is the same as the homotopy group of your quotient, meaning the paths through this quotient space you make. And then the amazing thing is the universal cover does not necessarily equal the space you started with. And like weirdly, musicians have been realizing some of these relationships in simple cases, but particular cases, but they've never seen all of it. So algebraic topology teaches us that the paths through a space can be divided into a boring part and an interesting part. The boring part is called the wide tree subgroupoid, and it's basically, you can think of it as a Euclidean, the Euclidean part of your space. And then the interesting part is the automorphism group, which is the loops that connect the point to itself. The automorphism group of a quotient space is a set of transformations connecting every point, every musical object to itself. It is the opposite group of the symmetry group. The two relate by a contravariant functor. And so all of this category thinking actually helps, because what the geometry delivers is not really geometrical, it's algebraic. It's a set of paths. And the cool thing about my new way of doing it is you can get these paths without having to do messy geometry. In the bad old days, I would be like describing higher dimensional simplexes and say, see, this face is glued to this face with this transformation. And I'd be using coordinates. And it was like, I have these papers that are really, really boring and really painful to read because it's all this geometrical detail. And the cool thing is, if you do ascend to this abstract level, you can skip all the detail and just do it with a line of algebra. Okay. So what the geometry fundamentally tells you, and now we're going to get back to music in an interesting way. What all of those quotient spaces I was messing around with, what they tell you fundamentally is that music has one more hierarchical level than we thought. And this is really the motivating idea in my second book. So this is a figure from chapter 1 of my second book. And down here is the chromatic scale, and it is the set of notes on the piano keyboard. And usually when we're making music, we are not operating directly with the chromatic scale. We're operating with some subset, which here is the white notes, right? So those white notes are this middle level, but usually we're not directly operating with all the white notes either. We are operating with some subset of those notes, which here are the C major triad. And so what the geometry fundamentally tells you, if you understand it abstractly enough, is that similar kinds of motion occur on all of these levels. So we can think of like do a deer. You all know do a deer, and that's moving a pattern up along the scale. Right? But we can take that same pattern and apply it at the top level of the triad. Or we can apply it at the lowest level, which is the, right? And it's the same structure, but it's occurring on all of these different levels, okay? So why is this important? This is important because musicians are habitually using these different levels in really intelligent ways. Here is a generic jazzy motive. Okay, that sounds like this. Right? Now, every jazz musician knows how to take that pattern and move it along all of those levels in the hierarchy. And you know how to do it too, even though you might not know the principles. Because if I play, you know that's wrong. Right? And so you kind of know that it should be. I remember talking to my student, a great jazz bassist, Gus. I said, Gus, why is the other one right? And he's like, I don't know, it just is, right? And that's that intuitive knowledge. What's really going on here is that this motive uses intervals from all three levels of the hierarchy, right? The basic notes C, G, and E are at that top level. The F sharp you get by projecting the G to the bottom level and going down one chromatic step. The F you get by projecting the E to the top level and going up one diatonic step, right? So everybody knows this. Normal musicians know, yeah, that lower one is a chromatic neighbor. The upper one is a diatonic neighbor. And in fact, some more theoretical musicians know it's a feature of Western music that lower neighbors tend to be chromatic and upper neighbors tend to be diatonic. That's why those other bogus ones didn't sound so good. But what's cool about my perspective is I've got a way of generalizing this. So normal intuitive musical knowledge covers only the traditional chords and scales in the Western canon. My way has generalized it to any chords you want. Literally, if you want to use 24 notes in the octave and 17 note chords, I've got you covered. The system works no matter what. And if you go back, you will look, obviously, what this is telling you is that a musical collection, a scale, is an object. And we need to be able to glue these objects to each other to form recursive hierarchies of arbitrary depth. And that is a really significant part of what musical knowledge consists in, is being able to navigate this hierarchy, which is just a little bit too complicated to work with in a completely intuitive way. What musical intuition is developing fluency with one or another specific configurations of this general architecture, okay? Okay, so one could represent a huge amount of music using the same transformations at every level. Basically, you have translations and reflections, the dihedral group operating at all three levels. This gives you a unified transformational language that really unlocks a lot of music. Translation occurs on multiple levels. A really cool point is that in Western music, repetition is the application of a symmetry. Of course, literal repetition is the application of the time translation symmetry. What we call a sequence is pitch translation. There's also translation through the ensemble, which creates permutations. So I'm just going to play these examples for you, and I'm conscious that I got a motor here. All right, that's literal repetition, which is a little bit boring. Now we're going to translate it through pitch as we repeat, and this gives you what's called a sequence. This one is amazing to me. I'm just going to permute the lines so we translate through the ensemble. And to me, it sounds like 1,000 times more interesting. And of course, you can do both of those at once. And this is the great discovery of the Baroque. There's actually one more symmetry that is really important in music, which is reflection, or turning music upside down. Nobody ever uses this in repetition, but it's in principle possible, and it sounds like this. It's really amazing. One measure of music generates all 6 of these measures by reflections and permutations. I would just like to toot my own horn and say I'm very proud of finding one pattern that works with all of these different symmetry combinations. That's basically what, that's a big part of compositional knowledge in the tradition. Okay, so we're almost done. I have written a little computer language for manipulating musical patterns. It's called Arca. It's really a set of Python modules, but I have a web interface. So here is a little bit of musical computer code. I said to someone who goes to this conference, I said, I'm not really a functional programmer. He said, I don't see any variables changing state. So So, I declare a scale, a motive, an accompaniment, and then I transform the scale. These are basically translations happening at different hierarchical levels. I do the same to the motive and the accompaniment. You press run. Okay, this is a big chunk, well, 32-bar chunk of a string quartet by Beethoven. We do not think of Beethoven as an algorithmic composer. That's the algorithm. My friend Mark Newman points out, so this is the upper bound on the Kolmogorov complexity of that chunk of Beethoven, right? So what's really cool is going through music, and so here's Chopin's E minor prelude, right? This is a simplification of Chopin's A minor prelude. It's 8 lines of code. It's not exactly note for note. To do note for note, you need 20 lines of code. But what's really cool is to think that this is the background structure that's a little simpler, and then he's tweaking it a little bit. All right. So this is something you can use compositionally. It's also something you can use to do this reverse engineering, essentially doing musical analysis by inventing computer programs that recreate the surface music. And you have to trust me, people did not think you could do this for Chopin and Beethoven and Mozart, and you can. People didn't think it was algorithmic because we didn't have a sophisticated enough sense of what the underlying hierarchical structure of music was. Okay, I thought that we shouldn't, you can also, the concept of a chord arguably arises over the 200-year period from like 1550 or 1500 to 1700, let's say, as musicians gradually discovered the right action dual to the left action symmetry group. We know they all manipulated these symmetries I was using in creating the repetitions. We know every composer consciously manipulated those. Those have a dual, a right action dual, and it basically, composers discovered the right action dual is most naturally described using this hierarchical picture and using the concept of the chord as a top level of hierarchy. That means the concept of a chord arose through a collective, unconscious, centuries-long group theory calculation. The musical discovery of the contravariant functor mapping an orbifold symmetry group to its homotopy group, which we can generalize to discrete cases. I'm going to end. The first improvisation we did was based on this piece I wrote 50 years ago, The Walking Dinosaur. And what I did in creating the variations of it is I assigned it a hierarchical structure where I said this note is not part of the underlying thing. It's one of these hierarchical neighbors. And this note depends hierarchically on this one. And that made the transformations interesting and non-obvious to the ear. So I think I'm going to stop there so that you have a chance to ask questions. There is a little bit more where this came from. I don't think that will surprise you, but I think this is a good resting point. So I'm going to say thank you, and I'll invite a couple questions, and then we'll have the rest of our concert. Anyone got a question? Okay, right there. Yeah, you.
So you showed earlier the tool for visualizing where the notes show up on the Mobius strip.
Yeah.
Which is really cool. And I'm wondering if you can go the other way around, where like you draw a curve through the Mobius strip and see what sound you get.
Yeah, absolutely. You absolutely can go, and that's a little bit what I was doing with Rudrash, and that's what you could do that with the dancer on the stage. So yeah, you can go 2 directions. The singularities are a pain, because you have to, there's different ways of bouncing off the boundary. There are 2 ways of bouncing off the boundary. So you need a way to specify which of those you have in mind. But yes, you can do both. And that's part of the cool thing. Another question? There was someone down here. Yeah, go.
Yeah, very nice talk. Thank you.
Thank you so much. And thank you.
You're basing the theory on like the piano.
No.
Well, okay, so here's my question. So can you derive the central thing based off the classical kind of intervals, fourths and fifths and thirds, which
Okay. Well, all right. I'm basing the thing off continuous frequency space, of which the piano is a discretization. So my spaces are continuous in the sense that that it's not based on the discrete piano, but it is based on the logarithm of the fundamental frequency. So you just asked another question about a different discrete space, what we call the tone nets, where maybe you have a grid of fifths in one direction and a grid of major thirds in the other direction, and a grid of octaves. And maybe if you're a just intonation guy, you've got the just seventh. The answer is you could not do that with the old geometry, because if you asked me that 10 years ago, I would have said, no, don't think that way. Think in terms of the logarithm of the fundamental frequency, because it's much more general. Once you categorify everything, yes, now we can do that same thing. And in fact, the forming of the quotient in that space you're talking about, the forming of a just intonation scale, it's just another quotient by just another symmetry group. Essentially, in continuous voice leading geometry, what I started with, you're forming the quotient by octave equivalence and you're gluing together octave relationships. And in this one, you're forming a quotient by comma relationships and you're forming scale degrees. But yes, so that's the big advantage of the category theory perspective, is we can now extend this way of thinking to those discrete spaces that existed, they originate with Euler, basically. Cool, great question. Yes?
Hi, that was really cool. And
Thank you again.
I'm really excited about I was wondering if you had considered at all the effect of metric position on what harmony is available.
Yeah, that's a great question. Let me just say there's everything you can say about pitch. Once you think in a properly categorical way, you realize that you can also say it about rhythm, and that those spaces, the second improvisation was supposed to say, the spaces are isomorphic. So there's a specific question: do harmonies depend on metric position? And something I've done that I didn't talk about at all, but is in this second book. By the way, these books are deliberately priced cheaply by OUP so that outsiders to the field of music can buy them, $35 or so. And they're very thick books. So on a per page basis, it's really a great deal. In this middle book, the second book, that's a fortune cookie. It's not a book. In the middle one, I have a giant corpus of 10,000 pieces where I've got the score and an annotation of the score. I did all the annotations myself, all the Mozart sonatas, all the Bach chorales. The answer is no, metric position doesn't affect what chords people use. The same chord, not as much, you would think, but it's because reversing metric position is a really profound thing. So like in every Mozart and Beethoven rounded binary form, like the one I recreated with Arca, basically the natural thing to do in the middle section is to reverse. Instead of going tonic on the strong beat and dominant on the weak beat, you switch it and go dominant on the strong beat and tonic on the weak beat. And that happens enough. So maybe there's a little bit of a bias for tonics on strong beats, but it's not like that interesting. It's like a 60-40 thing. And what are you going to do with that, right? That's not useful. So no one's going to bust you because you were at 52-48 instead of 60-40. Yes, go ahead.
When you showed that your notation compresses Chopin in some sense, I noticed that your notation has a lot of familiar music theory concepts in it.
Yeah.
Is that just a coincidence, or could there be like a more extreme form of compression that uses completely unfamiliar concepts but recognizes the musical intuition better?
Right. This is like a little bit like the machine learning question or something like that. I don't know. I devised my language so that I could manipulate music theory concepts, right? That's what I care about. There's a little bit, if you're compressing Chopin, you would kind of like to be compressing it in a way that plausibly correlates to something that he would have recognized, right? Like, I feel pretty confident that Chopin was using concepts like this. He had these patterns and he knew how to move the patterns around. if your compression is too extreme, it no longer produces an aha. Like when I wrote that program, I was like, oh, cool, right? And I actually went through 3 drafts where I compressed it more and more when I realized, oh, if I describe this note in this way, I don't have to have 3 variant patterns. I can do it with just 2 variant patterns. Oh, and if I describe it in this way, I can do it with 1. So I mean, I don't know. Yeah, this is always, I mean, it's a little mean, right? Here I am, I compressed Chopin for you, right? You want more? I could take the spaces out, right? Like, I mean,
the
so
insight that I'm looking for is some people are very musical, but they're not familiar with Western musical theory. So I was wondering if these people who are very musical and don't understand the theoretical stuff that you have there, do they have the same point of view as you do, but just different words for the same thing? Or
I believe, yeah. I believe the answer is yes. And so, like, that's what I was getting at with my student, or with the fact that that sounds right. That sounds right. That sounds a little weirder to a lot of these people who just are players, right? They might not know diatonic neighbor or whatever, but they can be like, no, you don't do it that way, you do it this way. And really, that was like my fundamental problem learning music, which is, you know, I want the principles. And even if I could sort of figure out, oh, you should do it that way, but not that way, that felt cheap or something, right?
And of course, I was blown away by the notation and the compression. I thought it was phenomenal.
I mean, it's nothing personal. You know, everyone here is entitled to their own opinion, and I long ago learned that you can't please everyone. So, but thank you. I was just kidding around. Okay, I should stop there because we still have a wonderful concert coming up. Thank you so much.